Hey guys, what's up? This video is about intermolecular forces.
Now, it's important to know the difference between intermolecular forces and intramolecular forces because the difference is quite important to understand both of them. Take the molecule H2O, for example, which is made out of 2 hydrogens and 1 oxygen through a covalent bond, meaning that they share electrons. Now, this is a chemical bond between all 3 atoms, which is intra. So now take intermolecular forces with that same molecule of H2O. Now there are 2. And now there's a little dotted line between the 2 different molecules, and this symbolizes an intermolecular force. So intermolecular forces are between 2 atoms of 2 different molecules, not within one molecule between different atoms. So the thing to remember here is that intermolecular forces are physical and they are between 2 different molecules.
So what do intermolecular forces do? Well, we know that they're physical bonds, meaning that they should influence physical properties. So physical properties like what? Well, first there's volatility, or the tendency to evaporate at 25 degrees Celsius. Then there's viscosity, or thickness. And then there's a couple others, such as surface tension, or state of matter, and melting or boiling point. There are 3 types of intermolecular forces. The first is London dispersion. The second is dipole-dipole, and the last one is hydrogen bonding, which you've actually already seen before. The first type is London dispersion forces. We will learn who or what molecules have them, what London dispersion forces are, what they're impacted by, and finally what they actually do. Firstly, who has them? And the answer is all molecules have London dispersion. So what are London dispersion forces? Well, remember what a molecular bond is, a covalent bond, meaning that they share electrons. And this explains London dispersion forces. Take nitrogen, for example. So nitrogen shares 6 electrons, as seen by the 3 bonds in the middle. And that means that sometimes the electrons may be over there, or sometimes they may be over there, because they are shared and they move to give each element an octet. This means that when the electrons move, they create temporary positive and negative charges, because the shared electron cloud means polarizability. Let me explain further. So take 2 nitrogen molecules in an intermolecular bond, symbolized by that dotted line. It is between the temporary positive end of one molecule and the temporary negative end of another molecule due to that covalent sharing within the molecule itself, because of that moving electron cloud.
Now, there are varying strengths of London dispersion forces, and one thing that impacts them is size. A bigger molecule equals a stronger LD, and this is because the electrons act over a larger surface area. There is more space for the electrons to move between the 2 different atoms in a compound, therefore creating more drastic positive and negative ends in the compound itself. Another thing London dispersion forces are impacted by is number of electrons. More electrons means a stronger London dispersion forces, and this is because more electrons means that a molecule is more polarizable, and that is the tendency of the electron cloud to distort or to move between the 2 atoms of a compound and create those positive and negative charges. So more electrons means more possibility for the electrons to move between the 2 atoms and create those positive and negative charges that are temporary and cause LDs. The second type of intermolecular forces are dipole-dipole forces, and who has them? And the answer is polar molecules. Now, if you remember, polar molecules are still covalent bonds, but what's important about them is that they have an unequal sharing of electrons, and this effect creates permanent positive and negative charges within the compound. Let me provide an example with hydrogen and fluorine. So in a compound, hydrogen will be positive and fluorine will be negative due to the difference of electronegativity. Fluorine wants the electrons more. And what that does is it creates a higher region of electron density around fluorine, creating permanent positive and negative charges within the molecule itself. It is polar. Dipole-dipole forces are impacted by electronegativity, which is how much an element in a bond pulls the electrons to itself. So a higher electronegativity succeeds in creating a higher dipole-dipole force because the pull between atoms of different elements is now stronger. So those permanent positive and negative ends now have more potent forces, attracting them to each other because opposite charges attract. And now, last but not least, we have hydrogen bonding, the strongest of all the intermolecular forces. And the molecules that have these are compounds that have a hydrogen and a fluorine, oxygen, or nitrogen, and they exhibit the hydrogen bonding forces with other compounds that have the same elements. And you've actually already seen this before. Where? Now, just you wait, because this is a very common molecule. You consume it every day. Mr. Z drank a mole of these in front of your very eyes. What could it possibly be? It's good old H2O, which, if you remember, has one oxygen, which is one of the elements needed for hydrogen bonding, like nitrogen and fluorine, and it also has a hydrogen. Now, remember those two water molecules at the beginning of the video? There was an intermolecular force between them, specifically a hydrogen bond between the positive hydrogen of one molecule and the negative oxygen of another. Or, if you replace an oxygen with a nitrogen or fluorine, it is a hydrogen bond. The strength of hydrogen bonding depends on electronegativity, which, if you remember, increases going up and across the periodic table, with fluorine having the highest electronegativity. So the highest electronegativity difference is in fluorine when bonding with a hydrogen in regards to oxygen and nitrogen. So what that means is that the strongest H bond is dependent on the atom with the highest electronegativity, because this creates more drastic positive and negative charges within the molecule and between different molecules. So fluorine has the highest and the most strength of hydrogen bonding, while nitrogen has the lowest due to this electronegativity difference. Finally, what do intermolecular forces actually do? Well, remember, they're physical bonds, and that means that they do influence physical properties. And these physical properties include volatility, viscosity, surface tension, melting point and boiling point, and finally, state of matter. Let's look at London dispersion forces with their state of matter. Remember that bigger molecules produce stronger London dispersion forces. So let's take a look at the diatomic elements with fluorine, bromine, and iodine, with the size increasing towards iodine, meaning that fluorine is very small and iodine is very big, which means that fluorine has the lowest London dispersion forces while iodine has the highest. And once again, that is the temporary positive and negative charges. And what this means is that the iodine atoms are more attracted to each other than the fluorine atoms are attracted to each other because of that difference in London dispersion forces. Greater attraction provides greater concentration, but has an impact on the state of matter. So iodine having more concentration is a solid, and fluorine having less concentration is a gas. Secondly, melting points by dipole-dipoles. Remember that a higher EN difference creates a higher polarity, creates higher dipole-dipole forces. Look at CO2 and SO2, for example. So SO2 exhibits dipole-dipole forces, meaning that its molecules are held more tightly together and have a greater resistance to being melted. So what are the melting points of these two molecules? Well, CO2 melts at negative 56.6 degrees Celsius. Well, SO2 melts at negative 72 degrees Celsius. So SO2 is obviously the stronger molecule due to its dipole-dipole forces, while CO2 is weaker with no dipole-dipole forces at all. Finally, surface tension with hydrogen bonding. So H2O is back, the molecule you know and love, along with hexane. So H2O exhibits hydrogen bonding, as you well know, but hexane does not, nor does it have DD. So remember, when you pour water out on a table, it actually has a little raised bump called surface tension because the molecules are attracted closely to each other. And here's that water on the table. So now when you pour hexane out onto a table, it has a habit of falling completely flat with no raised bump. And this is because it does not have any surface tension like H2O does. And once again, this is due to the absence of hydrogen bonding, that attraction between the molecules. So today we've learned about intermolecular forces, not intra, the difference between within and between molecules. We know there's 3 types, and finally we know their influence on physical properties. So thank you very much for watching, or spasiba in Russian, and have a great day of learning.